Isaac Newton, one of history's most celebrated scientific minds, was born on January 4, 1643, in the small village of Woolsthorpe, Lincolnshire, England. His arrival into the world was fraught with uncertainty. Born prematurely and so small that it was said he could fit into a quart mug, Newton's survival was nothing short of a miracle. His early life, marked by fragility and solitude, shaped a contemplative mind that would later transform humanity's understanding of the universe. Newton's father, also named Isaac, passed away 3 months before he was born. This loss cast a shadow over his early childhood, as his mother, Hannah Ayscough Newton, struggled to raise him as a young widow. When Isaac was just 3 years old, Hannah remarried a wealthy clergyman, Barnabas Smith, leaving Isaac to be raised by his maternal grandparents. This separation from his mother left a profound impact on the young boy, cultivating a sense of abandonment that would echo throughout his life. During his childhood, Newton displayed little outward promise of the genius he would become. Descriptions of him as a boy paint a picture of a quiet, solitary child with a penchant for building intricate mechanical toys and models. Among these were sundials and water clocks, early indications of his curiosity and ingenuity. Even as a child, Newton exhibited an intense focus on problem-solving, a trait that would define his intellectual pursuits. At the age of 12, Newton was sent to the King's School in Grantham, a nearby town, where he lived with an apothecary named William Clark. While in Grantham, Isaac's academic potential began to emerge. He showed an affinity for mathematics and a remarkable ability to grasp complex concepts. Nevertheless, his studies were interrupted in 1659 when his mother called him back to Woolsthorpe to manage the family farm. It quickly became apparent that Newton was ill-suited for the life of a farmer. His mind often wandered from the mundane tasks of rural life to more abstract problems. Recognizing his lack of interest in farming and his potential for greater things, his uncle, a Cambridge graduate, persuaded Hannah to allow Isaac to return to his studies. This decision would prove pivotal, redirecting Newton's life toward academic excellence. In 1661, at the age of 18, Newton entered Trinity College at the University of Cambridge as a subsizar, a role reserved for students who performed menial tasks in exchange for financial support. His early years at Cambridge were unremarkable academically, but the environment exposed him to the works of great thinkers such as Aristotle, Descartes, and Galileo. Newton's hunger for knowledge deepened, setting the stage for his later breakthroughs. The seeds of Newton's intellectual development were sown during this time, even if they were not immediately apparent to his professors. He was self-taught in many subjects, often delving into topics that extended beyond the university curriculum. Newton began keeping a personal journal, filled with notes and reflections on subjects ranging from mathematics to alchemy, foreshadowing the interdisciplinary breadth of his later work. Newton's early years were marked by personal struggles and an undercurrent of resilience. He overcame the challenges of a difficult family dynamic, rural isolation, and financial constraints to pursue his education. These formative experiences not only shaped his character, but also instilled in him a drive to seek answers to the world's deepest mysteries. As Newton transitioned from his modest beginnings in Woolsthorpe to the academic rigor of Cambridge, he carried with him an insatiable curiosity. While his childhood gave little indication of the revolutionary discoveries he would make, it laid the foundation for his methodical approach to understanding nature. In many ways, Newton's early life served as the quiet prelude to a symphony of scientific innovation. The story of Isaac Newton's beginnings is one of perseverance and potential. Though born into humble circumstances, his early life reveals the traits that would later define him: a relentless curiosity, a deep sense of solitude, and an unyielding determination. It is a testament to the power of resilience and the transformative potential of education, setting the stage for his ascent to scientific immortality. Isaac Newton's arrival at Trinity College, Cambridge, in 1661 marked the beginning of a transformative phase in his life. At the age of 18, Newton entered the institution as a subsizar, performing duties such as waiting tables and cleaning in exchange for financial assistance. Despite these humble beginnings, his time at Cambridge proved critical to shaping the intellectual foundations that would later define his extraordinary career. At the time, the curriculum at Cambridge was heavily influenced by the classical traditions of Aristotle, with a focus on rhetoric, logic, and scholastic philosophy. However, the intellectual landscape of Europe was beginning to shift, thanks to the works of thinkers such as Copernicus, Galileo, and Descartes. This burgeoning scientific revolution offered an alternative framework for understanding the natural world, one rooted in observation, experimentation, and mathematical precision. Newton's curiosity quickly gravitated toward these new ideas, even as he fulfilled the formal requirements of his education. One of the pivotal moments during Newton's early years at Cambridge was his exposure to the work of René Descartes. Descartes' meditations and principles of philosophy introduced Newton to the concept of a mechanistic universe governed by natural laws, an idea that would profoundly influence his thinking. Additionally, Newton delved into the works of Galileo, whose studies on motion and inertia provided a foundation for Newton's later formulation of the laws of motion. Newton's self-directed studies extended far beyond the prescribed curriculum. He immersed himself in mathematics, teaching himself the works of Euclid and discovering more advanced ideas from contemporary mathematicians such as John Wallis and Isaac Barrow, the latter of whom became one of Newton's mentors. It was during this period that Newton began to develop his own mathematical framework, laying the groundwork for what would later become calculus. Despite his growing intellectual prowess, Newton's initial years at Cambridge were relatively unremarkable in the eyes of his professors. He was introverted, rarely socialized, and preferred solitary contemplation to classroom discourse. However, this isolation allowed Newton to focus deeply on the problems that intrigued him, honing his ability to approach questions with unparalleled rigor and creativity. Newton's academic trajectory took a decisive turn in 1664, when he earned a scholarship that freed him from his subsizar duties and allowed him to devote more time to his studies. Around this time, he began keeping a series of notebooks, often referred to as his waste books. These notebooks contained detailed explorations of mathematical problems, mechanical principles, and alchemical experiments, offering a glimpse into the breadth of Newton's intellectual curiosity. One of the key breakthroughs during this period was Newton's realization that mathematics could be used to describe natural phenomena. This idea, which seems self-evident today, was revolutionary in Newton's time. His exploration of infinite series, tangents, and rates of change would eventually coalesce into the invention of calculus, a mathematical tool that provided the foundation for modern physics and engineering. Newton's studies at Cambridge also extended into the realm of natural philosophy, where he began questioning long-held assumptions about light and optics. Using rudimentary equipment, he conducted experiments that challenged the prevailing view of light as a homogeneous substance. These early investigations would later culminate in his groundbreaking theory of the composition of light. The intellectual environment at Cambridge, combined with Newton's insatiable curiosity, provided fertile ground for his development as a scientist. By the time he completed his Bachelor of Arts degree in 1665, Newton was no longer a mere student of established knowledge. He was beginning to generate ideas that would challenge and redefine the boundaries of human understanding. As Newton left Cambridge temporarily in 1665 due to the outbreak of the Great Plague, he carried with him a burgeoning sense of purpose and the seeds of revolutionary thought. His time at the university had not only exposed him to the leading ideas of the scientific revolution, but also encouraged him to forge his own path. These formative years were critical in transforming Newton from a curious student into a pioneering thinker, ready to tackle the mysteries of nature with unprecedented precision and insight. The Great Plague of 1665 forced Isaac Newton to leave Cambridge and return to his family home at Woolsthorpe Manor. This period of isolation, which stretched into 1666, could have been a setback for many. For Newton, however, it became an extraordinary phase of discovery and creativity, what he would later refer to as his Annus Mirabilis, or Year of Wonders. The seclusion provided Newton with uninterrupted time to explore his ideas, leading to groundbreaking advancements in mathematics, optics, and physics. During these years, Newton laid the foundations of calculus, a mathematical framework that would revolutionize science. He approached problems involving rates of change and areas under curves, concepts that were essential for understanding motion and other dynamic systems. By formulating his method of flux science, his term for calculus, Newton created a tool that would enable scientists to model natural phenomena with unprecedented precision. This work, though unpublished for decades, marked the beginning of a new era in mathematics. Newton's insights into optics also took a dramatic leap forward during his time at Woolsthorpe. Using prisms, he conducted experiments to study the nature of light and color. Contrary to the prevailing view that light was a uniform substance, Newton demonstrated that white light could be decomposed into a spectrum of colors and then recombined into white light. This groundbreaking discovery laid the foundation for his later work in optics and cemented his reputation as a pioneer in the field. Perhaps most famously, it was during this period of isolation that Newton began to formulate his theory of universal gravitation. Legend has it that Newton observed an apple falling from a tree at Woolsthorpe, prompting him to ponder the forces governing its motion. While the story of the apple has taken on mythical proportions, it reflects a profound realization. The force that causes an apple to fall to the ground is the same force that governs the motion of celestial bodies. Newton's insight into gravitation was part of a larger effort to unify terrestrial and celestial mechanics. He recognized that the same principles could explain both the motion of planets in their orbits and the behavior of objects on Earth. This realization challenged the long-standing division between earthly and heavenly phenomena, a divide that had dominated scientific thought since the time of Aristotle. The intensity of Newton's intellectual activity during the Plague Years was remarkable. Isolated from academic institutions and peers, he relied solely on his own ingenuity and determination. His solitary nature, which had often been a barrier to social and collaborative endeavors, became a strength, allowing him to focus without distraction. The ideas he developed during this period would later form the cornerstone of his scientific legacy. Despite the revolutionary nature of his discoveries, Newton kept much of his work to himself during these years. He was notoriously reluctant to publish his findings, fearing criticism and controversy. As a result, many of his insights, including his development of calculus, remained unknown to the broader scientific community for decades. This reticence would later lead to disputes over priority, most notably with Gottfried Wilhelm Leibniz, who independently developed calculus. The period of the Plague Years also provided Newton with time to explore his interests in alchemy and theology. While these pursuits are often overlooked in discussions of his scientific achievements, they were central to his intellectual life. Newton believed that understanding the natural world required an integrated approach, one that encompassed both scientific inquiry and spiritual reflection. His alchemical experiments, though rooted in mystical traditions, reflected the same meticulous attention to detail that characterized his scientific work. By the time the plague subsided and Newton returned to Cambridge in 1667, he was no longer the same student who had left 2 years earlier. He returned with a wealth of revolutionary ideas that would soon propel him to the forefront of scientific thought. The work he conducted in isolation at Woolsthorpe laid the groundwork for the monumental contributions he would make in the decades to come. The Plague Years stand as a testament to the power of individual creativity and perseverance. Isolated from the intellectual hubs of his time, Newton achieved a level of productivity and insight that remains unparalleled in the history of science. His Annus Mirabilis was not merely a personal triumph, but a turning point in humanity's understanding of the natural world, demonstrating the profound potential of the human mind when unbounded by convention or circumstance. Among Isaac Newton's most groundbreaking contributions to science was his work on optics, which fundamentally transformed the understanding of light and vision. His meticulous experiments, innovative methods, and bold conclusions challenged prevailing theories and laid the foundation for modern optical science. The period from the late 1660s through the early 1670s saw Newton delve deeply into this field, culminating in discoveries that were as controversial as they were revolutionary. Newton's fascination with light began during his student years at Cambridge and intensified during his time at Woolsthorpe. His experiments with prisms revealed that white light could be decomposed into a spectrum of colors, including red, orange, yellow, green, blue, indigo, and violet. This observation contradicted the dominant view, championed by thinkers like René Descartes, that white light was a uniform substance and that colors arose from modifications of this light. To test his ideas, Newton conducted a series of precise and innovative experiments. He directed a beam of sunlight through a triangular glass prism, observing how the light separated into its constituent colors. Importantly, he then used a second prism to recombine these colors into white light, proving that the colors were inherent properties of light itself, not products of the prism. This discovery formed the cornerstone of Newton's theory of color, which he described as the composition of light. Newton extended his investigations to understand the behavior of light as it interacted with various surfaces and materials. He observed phenomena such as reflection, refraction, and diffraction, meticulously documenting his findings. Among his key insights was the idea that light particles, or corpuscles, traveled in straight lines but could interact with surfaces in ways that explained their bending and scattering. Though later superseded by the wave theory of light, Newton's corpuscular theory was a critical step in the evolving understanding of optics. In 1672, Newton's reputation as a leading thinker in optics was solidified when he presented a reflecting telescope to the Royal Society. This innovative device, which used mirrors instead of lenses, resolved many of the issues associated with traditional refracting telescopes, such as chromatic aberration. Newton's telescope not only demonstrated the practical applications of his optical theories, but also marked a significant advancement in astronomical instrumentation. Despite the brilliance of his discoveries, Newton's work on optics was not without controversy. His conclusions about the composition of light challenged established theories and sparked heated debates among his contemporaries. Figures such as Robert Hooke and Christiaan Huygens opposed Newton's ideas, leading to acrimonious exchanges. Newton's sensitivity to criticism and his tendency to withdraw from public disputes only heightened the tension, reflecting the personal and professional challenges he faced during this period. Newton's contributions to optics extended beyond experimentation and theory. His publication of Optics in 1704 provided a comprehensive account of his discoveries and experimental methods. The book was organized into a series of queries, where Newton posed open-ended questions about the nature of light and its interaction with matter. These queries invited further investigation, reflecting Newton's recognition that science is an evolving process of discovery. A distinctive feature of Newton's work in optics was his ability to combine theoretical insight with practical experimentation. His rigorous approach exemplified the scientific method, emphasizing observation, hypothesis testing, and mathematical precision. This methodology not only advanced the field of optics, but also influenced the broader trajectory of scientific inquiry. Newton's optical research also intersected with his philosophical and theological beliefs. He viewed light as a fundamental element of creation, imbued with both physical and spiritual significance. This perspective reflected Newton's broader worldview, which sought to unify natural philosophy with divine principles. While his theological interpretations of light have largely faded from scientific discourse, they reveal the depth and complexity of his intellectual pursuits. In redefining the nature of light, Newton illuminated much more than the mechanics of vision. His work on optics demonstrated the power of careful observation and critical thinking to overturn long-held assumptions. By exploring the fundamental properties of light, Newton not only advanced human understanding of the physical world, but also inspired future generations of scientists to look beyond the visible spectrum, literally and figuratively, in their quest for knowledge. Isaac Newton's Philosophiae Naturalis Principia Mathematica, commonly known as the Principia, is one of the most significant works in the history of science. Published in 1687, it presented a comprehensive framework for understanding motion and gravitation, uniting celestial and terrestrial mechanics under universal laws. The Principia not only revolutionized physics, but also provided the mathematical tools necessary for the subsequent development of engineering, astronomy, and countless other disciplines. The origins of the Principia can be traced to Newton's correspondence with Edmund Halley, a renowned astronomer and member of the Royal Society. In 1684, Halley visited Newton in Cambridge to discuss the motion of celestial bodies. Newton shared that he had already calculated that planetary orbits would take the form of ellipses if they were governed by an inverse square law of attraction. Halley, recognizing the profound implications of this insight, urged Newton to formalize his ideas into a publishable treatise. Newton's response to Halley's encouragement was remarkable. Over an intense period of approximately 18 months, Newton expanded and refined his theories, producing a work of staggering scope and depth. The result was the Principia, a synthesis of mathematics, physics, and philosophy that would redefine humanity's understanding of the natural world. The Principia is divided into 3 books, each addressing a specific aspect of Newton's unified theory. Book I, titled The Motion of Bodies, lays the mathematical foundation for understanding motion. In it, Newton introduces his famous 3 laws of motion, which describe the relationships between forces and the movement of objects. These laws provided a universal framework for analyzing everything from falling apples to the trajectories of projectiles. Book 2 focuses on the motion of bodies in resisting mediums, such as liquids or air. This section explores the behavior of fluids, resistance, and the dynamics of objects moving through such environments. Though less celebrated than the other sections, Book 2 demonstrates Newton's commitment to addressing practical challenges in engineering and mechanics, expanding the applicability of his theories. The final and most renowned section, Book 3, is titled The System of the World. Here, Newton applies the principles outlined in the earlier books to celestial phenomena, explaining the motion of planets, comets, and moons. His law of universal gravitation, which posits that every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them, is introduced. This law unified the motions of the heavens and the earth, dismantling the long-held Aristotelian dichotomy between celestial and terrestrial realms. The publication of the Principia was not without challenges. Newton's disagreements with Robert Hooke, particularly over the priority of the inverse square law, nearly derailed the project. Hooke claimed to have proposed the idea before Newton, leading to bitter disputes. Edmund Halley played a crucial role in mediating the conflict and ensuring that the Principia was published. Halley even financed the publication himself, recognizing the monumental importance of Newton's work. The reception of the Principia was immediate and profound. It was hailed as a triumph of human intellect, providing a rigorous mathematical explanation for phenomena that had puzzled scientists for centuries. Astronomers, mathematicians, and philosophers across Europe marveled at its depth and scope. However, the Principia was not an easy read. Its dense mathematical formulations and abstract reasoning limited its immediate accessibility, even among educated audiences. Beyond its scientific impact, the Principia had profound philosophical implications. It introduced the concept of a mechanistic universe governed by natural laws, challenging religious and metaphysical explanations of the cosmos. Yet, Newton himself viewed his work as revealing the order and harmony of God's creation, bridging science and theology in ways that resonated with Enlightenment thinkers. The Principia Mathematica is more than a scientific masterpiece. It is a testament to the power of human reasoning and the pursuit of knowledge. By establishing the laws of motion and gravitation, Newton provided a unified framework that explained phenomena across scales, from the smallest objects on Earth to the vast motions of celestial bodies. His work laid the foundation for modern science, inspiring generations to explore, question, and uncover the fundamental principles that govern our universe. Following the publication of the Principia Mathematica in 1687, Isaac Newton's stature as a scientist and thinker reached unparalleled heights. His contributions to mathematics, physics, and astronomy had established him as one of the preeminent intellectuals of his time. Despite his fame, Newton remained at Cambridge for several more years, continuing his research, mentoring students, and navigating the complexities of academic life. This chapter explores Newton's later years at Cambridge, a period marked by further scientific contributions, growing administrative responsibilities, and the challenges of interpersonal relationships. After the Principia, Newton's academic work continued, albeit with less intensity than during his earlier years. His intellectual energy began to shift away from pure scientific discovery toward broader questions in philosophy, alchemy, and theology. Newton became deeply involved in exploring the nature of existence, time, and the divine, blending his scientific reasoning with metaphysical and spiritual inquiry. These pursuits, often conducted in secrecy, reveal a multifaceted thinker whose interests extended far beyond the boundaries of conventional science. Newton also assumed increasing administrative responsibilities at Cambridge, serving as Lucasian Professor of Mathematics. His lectures were highly technical and often inaccessible to students, reflecting Newton's tendency to focus on advanced and esoteric topics. Nonetheless, his position allowed him to influence the academic curriculum, encouraging a greater emphasis on mathematics and experimental philosophy, which he believed were central to understanding nature. Despite his academic achievements, Newton's years at Cambridge were not without personal and professional challenges. His relationships with colleagues were often strained, fueled by his sensitivity to criticism and a tendency toward isolation. The disputes that arose following the publication of the Principia, particularly with Robert Hooke, left lasting scars on Newton's psyche, contributing to his withdrawal from public engagement. One of the most significant developments during this period was Newton's election as a Member of Parliament, MP, for the University of Cambridge in 1689 and again in 1701. While his time in Parliament was relatively uneventful, records suggest he spoke only once to complain about a drafty window. It marked a shift in his career, reflecting his growing interest in public service and national affairs. This role also brought Newton into contact with influential figures in politics and finance, laying the groundwork for his later roles outside academia. Newton's later years at Cambridge were also marked by his growing involvement in alchemical studies. Alchemy, which sought to transform base metals into gold and uncover the secrets of eternal life, was considered by many to be a pseudoscience. Yet, Newton approached it with the same rigor he applied to his scientific work, meticulously recording his experiments and theories in extensive manuscripts. For Newton, alchemy was not merely about material transformation. It was a pathway to understanding the fundamental principles of nature and the divine order. Theological inquiry also became a central focus for Newton during this period. A devout but unorthodox Christian, he rejected the doctrine of the Trinity, a stance that placed him at odds with mainstream Anglican beliefs. Newton's writings on theology, which remained largely unpublished during his lifetime, reveal a deep commitment to uncovering what he considered the true teachings of the Bible. His meticulous study of biblical texts and historical records reflected the same analytical rigor that characterized his scientific endeavors. By the late 1690s, Newton's relationship with the University of Cambridge began to wane. The intellectual environment, once a source of inspiration, became increasingly stifling for Newton, who sought new challenges and opportunities. His growing fame and connections in political and financial circles made the prospect of a broader role outside academia increasingly appealing. In 1696, Newton resigned his post at Cambridge to accept the position of Warden of the Royal Mint, a role that marked a significant departure from his academic career. This transition was facilitated by his political connections, particularly his friendship with Charles Montague, Earl of Halifax. Newton's departure from Cambridge was both a personal and professional turning point, signaling the end of an era dominated by intellectual inquiry and the beginning of a new chapter focused on public service and practical applications of his talents. Newton's later years at Cambridge encapsulate the complexities of his character and career. While he achieved extraordinary success as a scientist and academic, this period also revealed his vulnerabilities, including his struggles with criticism, isolation, and the limitations of institutional life. Yet, even in the face of these challenges, Newton's time at Cambridge laid the foundation for his enduring legacy, demonstrating the breadth of his intellect and the depth of his commitment to understanding the natural world. This chapter of his life reflects a thinker in transition, poised to leave the cloistered halls of academia for the broader stage of public life. In 1696, Isaac Newton made a dramatic transition from the academic world of Cambridge to the practical and political sphere of London, taking up the role of Warden of the Royal Mint. This position, which would later lead to his promotion as Master of the Mint in 1699, marked a significant shift in Newton's career. Though initially perceived as a sinecure, the role became an arena where Newton applied his intellectual rigor and problem-solving skills to address one of England's most pressing challenges: the reformation of its coinage system. The late 17th century was a period of economic instability in England, characterized by rampant counterfeiting and the debasement of coinage. Coins were often clipped or shaved for their precious metal content, reducing their intrinsic value and undermining public confidence in currency. As Warden of the Mint, Newton was tasked with overseeing the Great Recoinage of 1696, an ambitious and complex effort to replace the debased currency with new, standardized coins. Newton approached this challenge with characteristic determination and analytical precision. Drawing upon his mathematical expertise, he implemented methods to ensure that the new coins were uniform in weight and composition. He introduced mechanical innovations, such as milling the edges of coins to prevent clipping, a practice that remains in use today. These measures significantly enhanced the security and integrity of the nation's currency, restoring public trust and stabilizing the economy. In addition to his administrative duties, Newton took an active role in combating counterfeiting, a crime that was punishable by death in 17th century England. He conducted meticulous investigations, personally interrogating suspects and compiling detailed evidence for prosecution. Newton's efforts in this regard were remarkably effective, leading to the conviction and execution of several notorious counterfeiters. This unrelenting pursuit of justice highlighted a lesser-known aspect of Newton's character: his resolve and capacity for decisive action when faced with societal challenges. Newton's work at the Royal Mint extended beyond technical and legal matters. He also played a crucial role in shaping economic policy, advising the government on issues such as the value of silver and gold. His recommendations were informed by a deep understanding of monetary theory and the dynamics of international trade, reflecting his ability to apply theoretical knowledge to practical problems. Despite his successes, Newton's tenure at the Mint was not without controversy. The transition from the old to the new coinage was fraught with logistical difficulties, including shortages of silver and public resistance to the new system. Newton faced criticism for the disruptions caused by the recoinage, but he remained steadfast in his commitment to the project, convinced of its long-term benefits. His perseverance paid off, as the reforms ultimately strengthened England's financial system and contributed to its emergence as a global economic power. Newton's role at the Mint also brought him into contact with some of the most influential figures of his time, including politicians, financiers, and members of the aristocracy. These interactions expanded Newton's sphere of influence and solidified his reputation as a polymath capable of excelling in both scientific and administrative domains. His position as Master of the Mint, which he held until his death in 1727, provided him with financial security and social prestige, elevating him to the status of a national figure. One of the remarkable aspects of Newton's work at the Mint was his ability to adapt his intellectual approach to a completely new context. While his earlier achievements were rooted in abstract reasoning and theoretical exploration, his contributions at the Mint demonstrated his capacity to address practical and operational challenges with equal proficiency. This versatility underscores the breadth of Newton's talents and his enduring impact on multiple fields. Newton's tenure at the Royal Mint also had a personal dimension. The demands of his role required him to relocate to London, where he lived at the heart of England's political and economic life. This move marked a departure from the relative isolation of his earlier years, exposing Newton to a wider array of experiences and relationships. While he remained a private and introspective individual, his work at the Mint reflected a deeper engagement with the broader societal issues of his time. In many ways, Newton's achievements at the Royal Mint exemplify his extraordinary capacity to integrate intellect with action. His reforms not only addressed immediate economic challenges, but also established lasting principles of currency design and management that influenced monetary systems worldwide. This chapter of Newton's life demonstrates that his genius extended far beyond the realm of science, encompassing a profound ability to effect change in the practical and institutional domains of human endeavor. Isaac Newton's appointment as president of the Royal Society in 1703 marked the beginning of a new phase in his life, one characterized by institutional leadership and the consolidation of his legacy. The Royal Society, founded in 1660, was England's premier scientific institution, dedicated to the advancement of knowledge through experimentation and debate. As its president, Newton brought both his intellectual prestige and his administrative acumen to the role, shaping the society's direction and influence for decades to come. Newton's presidency came at a pivotal time in the history of science. The Enlightenment was gaining momentum, with scholars across Europe challenging traditional views and seeking empirical explanations for natural phenomena. The Royal Society served as a hub for these intellectual exchanges, and Newton's leadership helped position the institution at the forefront of this movement. His reputation as the author of the Principia Mathematica lent the society an unparalleled authority in scientific matters. One of Newton's first priorities as president was to enhance the society's credibility and rigor. He instituted stricter standards for membership, ensuring that only those who made genuine contributions to science were admitted. This move elevated the society's status as an elite body of scholars and practitioners, fostering a culture of excellence and innovation. Newton's own work set a high benchmark, inspiring members to pursue ambitious research agendas. Under Newton's leadership, the Royal Society became a focal point for the publication and dissemination of scientific knowledge. He played a crucial role in overseeing the Society's journal, Philosophical Transactions, which provided a platform for groundbreaking discoveries and debates. Newton's involvement ensured that the journal maintained high standards, and he often influenced which works were published, reflecting his desire to shape the scientific narrative of his time. One of the most significant events during Newton's presidency was his handling of the long-standing controversy over the invention of calculus. The dispute between Newton and the German mathematician Gottfried Wilhelm Leibniz had escalated into an international debate, with both men claiming priority for the discovery. As president, Newton used his influence to bolster his case, commissioning a Royal Society report that largely vindicated his position. While this move solidified Newton's legacy, it also highlighted his competitive nature and his sensitivity to challenges to his intellectual authority. Newton's presidency was not without its critics. Some accused him of using the society to further his own reputation and settle personal scores. His disputes with Robert Hooke, a fellow member of the society, exemplify this dynamic. Hooke, who had been a vocal critic of Newton's theories, clashed with him on numerous occasions. Newton's dominance in the society ultimately marginalized Hooke and others who opposed him, reflecting both the advantages and the limitations of his leadership style. Despite these controversies, Newton's tenure as president was marked by significant achievements. He supported pioneering research in fields ranging from astronomy to chemistry, fostering an environment where experimental science could flourish. His influence extended beyond the society, shaping the broader scientific community and reinforcing the principles of empiricism and mathematical rigor that he championed throughout his career. Newton's role as president also had a symbolic dimension. By presiding over the Royal Society, he embodied the ideals of the scientific revolution: reason, inquiry, and the pursuit of knowledge. His leadership helped legitimize science as a cornerstone of modern society, challenging traditional authorities and laying the groundwork for the technological and intellectual advancements of the 18th century. Newton's presidency lasted until his death in 1727, making him one of the longest-serving leaders in the society's history. During this time, he navigated the complex intersection of science, politics, and public life, leveraging his position to advance not only the Royal Society's mission, but also his own vision for the role of science in society. His ability to bridge these domains reflects his versatility as a thinker and leader. In many ways, Newton's presidency at the Royal Society represents the culmination of his career. It allowed him to shape the direction of scientific inquiry on a national and international scale, ensuring that his influence extended far beyond his own discoveries. This period of his life underscores his enduring commitment to the advancement of knowledge and his belief in the transformative power of science. Through his leadership, Newton not only solidified his own legacy, but also laid the foundation for the continued growth of scientific institutions and ideas. The final years of Isaac Newton's life were marked by a profound consolidation of his intellectual achievements, a gradual retreat from public life, and an increasing engagement with questions of faith and personal reflection. By the time he reached his 60s, Newton had become not only the most influential scientist of his era, but also one of the most revered figures in the intellectual world. Yet, these years also marked a time of physical decline, deepening introspection, and philosophical exploration, as Newton moved toward the twilight of his extraordinary career. Newton's health began to deteriorate in the early 1720s. While his mental faculties remained sharp, his physical condition weakened considerably. He suffered from a series of ailments, including digestive issues and insomnia, which often left him feeling frail and exhausted. Despite these physical challenges, Newton continued to work, writing, and maintaining correspondence with other scholars. His dedication to his intellectual pursuits remained unwavering, though his output diminished significantly as he grew older. One of the most notable aspects of Newton's final years was his increased involvement in theological and alchemical studies. Although he had spent much of his earlier career focusing on mathematics and physics, later in life, Newton turned his attention to subjects that would have been considered more esoteric by the scientific community. He became deeply engrossed in the study of biblical prophecy, attempting to decode the hidden meanings of the Bible. Newton's theological works, many of which were unpublished during his lifetime, reveal his conviction that the natural world and the divine were interconnected, and that understanding one could lead to deeper insights into the other. Alongside his religious inquiries, Newton continued his alchemical experiments. His fascination with alchemy was not solely motivated by a desire to create gold, but rather a quest for deeper knowledge about the underlying principles of nature. Newton viewed alchemy as a spiritual pursuit, one that might reveal the hidden forces governing the universe. His extensive alchemical writings, which were often written in a code to prevent others from understanding his work, were only fully deciphered many years after his death, shedding light on this lesser-known aspect of his intellectual life. In addition to these personal pursuits, Newton's public role continued to evolve. Despite his declining health, he remained the president of the Royal Society, a position he held until his death in 1727. His leadership, however, was now more symbolic than active, as younger scientists took on greater responsibilities within the institution. Yet even as a figurehead, Newton's influence remained immense. The Royal Society continued to thrive under his auspices, fostering new generations of scientists who built upon the foundations he had established in mathematics, physics, and astronomy. By the mid-1720s, Newton's reputation as a scientist was unassailable, but the controversy over his legacy continued to simmer. His work in mathematics, particularly the priority dispute with Gottfried Wilhelm Leibniz over the invention of calculus, had left a lasting mark on his career. Though Newton had been vindicated by the Royal Society's 1712 report, tensions surrounding the issue still lingered, and some historians argue that the bitter rivalry may have affected Newton's interactions with others in the scientific community. Nevertheless, Newton's accomplishments in the realms of motion, gravity, and optics were universally acknowledged, and his theories formed the bedrock of modern physics. In his later years, Newton also became increasingly aware of his own legacy. He was often described as humble and modest, yet his writings and letters reveal a man who was deeply conscious of the historical importance of his work. Newton's sense of mission extended beyond personal ambition, and he believed that his discoveries were divinely inspired and part of a grand plan to unlock the mysteries of the universe. In his own words, Newton viewed himself as merely standing on the shoulders of giants, acknowledging the contributions of those who had come before him while simultaneously asserting his central role in the scientific revolution. Newton's death in 1727 marked the end of an era in science. He passed away in his sleep at the age of 84, a remarkable age for someone who had lived through the tumultuous years of the scientific revolution. His funeral was attended by many of the leading figures of British society, and he was buried in Westminster Abbey, a fitting tribute to the towering figure he had become. Yet, while his physical presence was gone, Newton's intellectual legacy continued to shape the course of science for generations to come. Isaac Newton's legacy is one of intellectual revolution. His laws of motion and universal gravitation formed the foundation for classical mechanics, influencing not only physics but also engineering, astronomy, and other sciences. His work in mathematics, particularly his invention of calculus, provided the essential tools for the study of change and motion. His groundbreaking investigations in optics reshaped our understanding of light and color. More broadly, his methodological approach to scientific inquiry, emphasizing observation, experimentation, and mathematical reasoning, became the model for future generations of scientists. Yet, Newton's influence extends beyond the boundaries of science. His belief in the unity of the natural world and the divine, his commitment to rigorous inquiry, and his understanding of knowledge as a continuous, cumulative process helped lay the groundwork for the intellectual movement of the Enlightenment. His ideas resonated with thinkers such as Voltaire, John Locke, and Immanuel Kant, who saw in Newton's work a model for how human reason could unlock the secrets of the world and advance human progress. Isaac Newton was not merely a scientist. He was a visionary whose ideas transcended the boundaries of his time. His work reshaped not only the scientific world, but also the way humanity understood itself and its place in the cosmos. Though his life was marked by personal struggles, controversies, and moments of doubt, his intellectual contributions have endured, making him one of the most influential figures in human history. In the centuries following his death, Newton's work has continued to inspire and challenge new generations of thinkers, ensuring that his legacy remains a central part of the intellectual history of mankind. The legacy of Isaac Newton remains one of the most profound in the history of science. His work fundamentally transformed human understanding of the natural world, shaping the trajectory of scientific progress for centuries. Beyond his contributions to physics, mathematics, and astronomy, Newton's influence extends to modern thought, philosophy, and the very framework of scientific inquiry. This final chapter reflects on Newton's lasting impact on both science and society, examining how his groundbreaking discoveries continue to influence contemporary thought and the evolving narrative of scientific progress. One of Newton's most enduring contributions was the establishment of the laws of motion and universal gravitation. His Philosophiae Naturalis Principia Mathematica, or Principia, outlined a comprehensive framework for understanding the forces that govern the movement of objects, from the fall of an apple to the motion of celestial bodies. The law of universal gravitation, postulating that every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, provided a unifying principle that explained phenomena as diverse as planetary motion and the behavior of tides. Newton's laws laid the foundation for classical mechanics, shaping the development of physics for over 200 years. Newton's contributions to mathematics are equally transformative. His invention of calculus, developed independently from Gottfried Wilhelm Leibniz, revolutionized the study of change and motion. The mathematical tools he developed for understanding instantaneous rates of change allowed for precise analysis in physics, engineering, and economics. While the priority dispute over calculus has become part of the historical narrative, there is no question that Newton's version of calculus was central to the development of modern mathematics. The application of calculus in understanding motion, growth, and optimization remains a cornerstone of scientific inquiry today. In addition to his work in mechanics and mathematics, Newton's studies in optics reshaped our understanding of light. His discovery that white light is composed of a spectrum of colors was revolutionary, as was his development of the theory of color based on the nature of light rather than the prevailing notion of color as a property of objects themselves. Newton's work in optics not only laid the foundation for the field of modern optics, but also contributed to the development of the telescope and other instruments that would become essential to the advancement of astronomy. His book Optics stands as a testament to his pioneering research in this area. Newton's methodology, often referred to as the scientific method, was another of his lasting contributions. While he was not the first to adopt empirical methods, he was one of the most influential in establishing the framework of observation, experimentation, and mathematical reasoning that would define modern science. His insistence on empirical evidence and mathematical rigor became the hallmark of scientific inquiry, influencing thinkers such as Galileo, Kepler, and later, figures like Albert Einstein and Niels Bohr. Newton's approach to science, centered around the idea that nature could be understood through the application of reason and experimentation, set the stage for the Enlightenment and the rise of modern scientific disciplines. Beyond his direct scientific contributions, Newton's work had a profound impact on philosophy and the broader intellectual climate of the Enlightenment. His natural philosophy, which sought to explain the workings of the universe through reason and observation, resonated deeply with Enlightenment thinkers. His emphasis on rationality and empiricism provided a model for intellectuals like John Locke, Voltaire, and Immanuel Kant, who saw in Newton's methods a pathway to understanding not just the physical world, but also human society and governance. Newton's influence on philosophy extended beyond the confines of his scientific work, laying the groundwork for a broader intellectual movement that championed reason, progress, and the potential of human thought. In the centuries following his death, Newton's ideas continued to shape the course of scientific and technological progress. His laws of motion and gravitation remained foundational until the early 20th century, when Albert Einstein's theory of relativity provided a more comprehensive understanding of space, time, and gravity. Despite this, Newton's laws are still used in everyday applications, from engineering to space travel, demonstrating their enduring relevance. The accuracy and simplicity of his laws make them essential tools for solving problems in a variety of fields, and they remain central to the education of physicists and engineers worldwide. Newton's influence also extended to the development of modern economics. The application of his mathematical principles to the study of motion and optimization found an echo in economic theories, particularly in the works of Adam Smith. The use of mathematical models to predict behavior and outcomes in complex systems, a practice that traces its roots back to Newtonian mechanics, has become a cornerstone of economic thought. The ability to model economic processes using the tools of mathematics reflects the broad applicability of Newton's approach to understanding the world, extending his influence beyond the natural sciences. Moreover, Newton's work at the Royal Mint and his influence in shaping British monetary policy provided a model for the integration of science with public service. His work in reforming the English coinage system not only restored the integrity of the nation's currency, but also demonstrated the practical application of scientific principles in governance. Newton's engagement with the practical challenges of statecraft, economics, and industry reveals the potential for scientific minds to contribute to broader societal advancement, a legacy that continues to inspire the integration of science and public policy today. Newton's personal life, though marked by periods of isolation and occasional disputes with colleagues, also contributes to his enduring legacy. His intense focus on his work, often at the expense of personal relationships, and his almost obsessive drive for perfection reflect the qualities of a man deeply committed to the pursuit of knowledge. His willingness to challenge prevailing ideas and his ability to synthesize vast amounts of information into coherent theories exemplify the qualities of intellectual curiosity and rigor that continue to define successful scientific endeavors. Newton's legacy is not just in his discoveries, but in the way he exemplified the intellectual virtues of persistence, vision, and a relentless quest for understanding. In conclusion, Isaac Newton's impact on science and society is immeasurable. His discoveries transformed our understanding of the universe and provided the tools for subsequent generations to build upon. His work laid the foundations for fields as diverse as physics, mathematics, astronomy, and economics. Beyond his specific scientific contributions, Newton's intellectual legacy also shaped the development of modern scientific methodology, philosophy, and public policy. As both a scientist and a thinker, Newton exemplified the potential of human reason to unlock the mysteries of the universe, and his legacy continues to inspire and inform the work of scientists, philosophers, and thinkers around the world. Through his genius, Newton has left an indelible mark on the course of human history, ensuring that his name will remain synonymous with scientific discovery and intellectual achievement for centuries to come.